Okay, so today we are talking about rational exponents, and this may be something that you've only been introduced to one time, which was back in Algebra 2, or maybe if you had college algebra. So it's funny that they consider this like review, but you've only, you've learned it once, okay? I hardly call that review. Just to remind you, we can say the square root of x. There's a little 2 inside that index there, but we can write it in using another notation, equivalent notation. This is x to the first power. And so we can rewrite this using rational fractional exponents, all right? If I were to rewrite this using rational fractional exponents, what would it be? X to the 1/2, very good. And if you had like the cubed root of x to the 5th, that could be rewritten as x to the 5/3. Very good. And so if we have the ith root, I for index, of x to some power p, we could rewrite that as p over I. And I like to do it that way, power over index, because of magnum pi, and that's just how I remember it. P over I, pi, magnum pi, yeah? Okay. So power over index. Now here you'll notice I wrote this power underneath the radical, but technically it's equivalent to say the ith root of x all to the p power. That would be the same thing. So either of these ways to write it is okay. Now I prefer this way because typically if you're trying to simplify something, it's easier to make it smaller first, because that's what radicals do. They're going to make things smaller, and then raise it to some power. Versus on this one, if you make it really big first by doing x to the, or like 25 to the 5th power, huge number. And then if I try to take the square root of that makes it really hard, okay? So I think this is usually how we'll evaluate things. But I just wanted to remind you that we can use rational exponents, and it's power over index, pi. And we're going to play with that just a little bit. So example 1, evaluate each expression without a calculator. It says without a calculator, but of course you're allowed to use a calculator. And I encourage you to use a calculator. There's no letters in that. Since there's no letters, of course you can use a calculator and use it to check your answer. So absolutely, in this class, if you have a calculator, get it out. I'm going to show you always how to check your answers using the calculator. And that's really useful on a test, to be able to use your calculator to check your work. Evaluate each expression without a calculator. There's also a multitude of ways that we can simplify these expressions. These are numerical expressions, number expressions. Just have numbers. We're just going to do it one way together, but again, there's lots of different ways to do this, and they're all equally valid. All right, so evaluating without a calculator. So we have negative 32 quantity to the negative 4/5 power. What would you guys like to do first? Okay, so I hear two things. Magnum pi, so you want to convert to a radical form? Okay, and then I hear negatives as well. Okay, I'm going to go with this negative. Negative exponents can get confusing. Like, where does that negative go if I convert to radical form? I'm not too sure. So I'm going to start by flipping this. He's unhappy up here in numerator land. So I'm going to do 1 over. Now I have negative 32 to the 4/5 power. And that's a little better. And now I definitely am going to go ahead and convert to radical form. So because for most of us, that's easier to evaluate when they're under radicals. If you can do it without, fantastic. I've been doing this for 20 years. I can do it without converting. But until you get there. So this is pi, power over index. So this is going to be negative 32 underneath a radical. What goes in the index? 5. And then the power is going to be 4. You'll notice how I wrote that because I'm going to make this smaller first. What is the fifth root of negative 32?
2. Negative 2.
How about, negative 2. Very good. Negative 2. Yes, this would be the fifth root of negative 2 times negative 2 times negative 2 times negative 2 times negative 2. There's 5 of them. One winner comes out. Okay? And then we need to take that negative 2 and raise it to the 4th power. And negative 2 to the 4th becomes positive 16. Again, that's negative 2 4 times, which because we got a even number of negative signs, that's going to turn positive. So this is a great answer. And it's an answer that you can absolutely check on your calculators. No matter what calculator you have, it's going to work. I'm going to type it in just like it is on my 84, negative 32 to the. Now, if you have pretty print, this is pretty print where you can see there's a little box. It's clear that it's an exponent. I used the caret key. This one doesn't have that. Negative 32, caret, again, the little caret symbol. The Casio, I need to, I'm trying to get it in the right spot where you can kind of see it. There we go. On this Casio model, I'm going to make sure that my entire power is in parentheses so that it's very, very clear that that whole thing is part of the exponent. Up here, I don't actually need that. So I can just do negative 4/5, 4 divided by 5. And you'll see that they both term out to the same decimal, and that's very good. Now, here's the best part. All of these calculators have convert to a fraction, math frac. On the TI, there's the math button right here. You push the math button, and the very first thing is convert to a fraction, number 1, and enter. On the Casio, it's even easier. Fraction to decimal button is right here. You just push fraction to decimal, and it says 1 with a little kind of interesting sort of bracket. That's 1 over 16. Math, the math button right here, and it's convert to fraction. Math frac. So I'm always going to walk around and be like, math bracket. All right. All right. All right. Looking at letter B. What do you want to do first?
Flip it.
Flip it. Yeah, we got a negative exponent. Now, the difference here is this one was not necessarily what we would call a traditional fraction, but could I take negative 32 and make it a fraction?
Yeah.
Yeah, so we did in fact flip the fraction. When we have an entire fraction like this, it's the reciprocal, so both things are going to flip. So I'm going to flip that fraction. My question is, what happens with the negative? Let's see. What does that mean when we have that negative out there? Is it unattached?
For the whole thing.
It's for the whole thing. Could it be for one of the things or both things?
Both.
Both? Is it both? Okay. It's pick one. All right. So what I'm going to do is I'm typically going to put my negative with the top number so that there's only one. I can't put it in both places. Why can't I put it top and bottom?
You can put it in the middle because then that would be positive.
Yeah, if it was negative divided by negative, it'd be positive, and we just changed our problem completely. So I'm always just going to put it with one of them. Out in front is kind of random, especially when we're working with radicals. So not going to do that. So now we are to a happy 1/3 power. And what is this 1/3 power affecting? Everything, yeah. Everything. Each same top and bottom. Any other question? I flipped the fraction, yeah, because of the negative. So that either creates a fraction like it did here, or it's really just. I'm sorry, what's the question? I heard negative 3/5.
Oh, I was just like.
Oh, reducing? I don't think so.
How come in the first one, the 4/5 only applied to the bottom, and the second one is for the entire thing?
So, good question. So the question was, how come the 4/5 only applied to the 32 and not this whole fraction? Well, in fact, it could have. So if I take my fraction negative 32 over 1 and then flip it, it'd be 1 over, negative 32. Let me put that negative on the bottom. Or on the top, doesn't matter. Negative 32. To the 4/5 power. Okay, what is that 4/5 affecting? Everything. So 1 to the 4/5 over negative 32 to the 4/5, still true statement, still true. Okay. But what is the 5th root of 1 to the 4th power? 1. Okay. So it does actually affect both. So it's a really good question. It's just that 1 to the 4/5 is just 1 anyway. Okay. Does that kind of make sense?
Yeah.
All right. So this 1/3 affects top and bottom. So I'm going to go ahead and say negative 27 to the 1/3 power. And we have 125 to the 1/3 power. Again, you can think this is power raised to a power. You'd multiply those powers. And 1 times 1/3 is 1/3. And then I am going to go ahead and think about rewriting this. This is the cubed root of negative 27 over the cubed root of 125. What is the cubed root of negative 27? Negative 3. And what is the cubed root of 125? 5. Good. All right. Oh, isn't the answer 3/5? So yes, that was correct. Negative 3/5. Again, this is something you could check on your calculator. Always a good thing to do. Any more questions on those? All right. Let's turn it on. Example 2. Oh, but I just said we're done. Example 2. Simplify each radical expression. You do have more properties on page A19. If you want to take a picture of those, that's always a good plan, or just look at them. You probably know most of those properties, but we want to simplify these radical expressions. You'll notice that we are not multiplying or dividing. We are adding and subtracting. And if we're going to add and subtract, then they must be like radicals. So they need to be made up of the same parts, like 2x plus 5x. These would be like terms. 2x plus 5x is 7x. 3 radical 5s plus 8 radical 5s is 11 radical 5s. So as long as they're made up of the same thing, then all we have to do is add those coefficients or subtract those coefficients, the numbers in front. In order to do that on something like this, are these like radicals? No, they're not like radicals. They don't match. So we want to think about trying to simplify first. So we're going to go back to what we did yesterday and think about simplifying those radicals, breaking them down. All right, so my math is not awesome. Oh, see, 245 divided by, I know 245 is divisible by 5. Okay, so I'm going to take this first radical expression here. 11 times the square root of 245 turns out is 5 times 49. And then 49 breaks apart into, 7 times 7. Then x cubed, this is a square root. I'm going to break apart x cubed into x squared times x to the first. Is that okay? Okay. And I'm going to try to simplify. What simplifies from this radical?
7.
All right, the 7 gets to come out. So we have 11 times 7. And the x squared. What's the square root of x squared? Just x?
Absolute value.
absolute value of x. I threw this one in? Yeah. And then what's left inside is a 5x. So I'm just going to clean that up. 11 times 7 is 77 square roots of, or sorry, not square roots, absolute value of x, radical 5x. Very complicated expression there. Now, I'm also going to do the same thing. I'm going to take this second expression. You'll notice how I included the negative in it. Negative 9 times the square root of 45x cubed. What does 45 break apart into? 5 times 9, and 9 breaks into 3 times 3. X cubed is going to be x squared times x to the first. So what gets to escape the radical? Pair of 3's, so a 3 gets to come out. And what's the square root of x squared? Just x? Absolute value of x. Very good. We got a 5 and an x left underneath the radical. So that turns into negative 9 times 3, negative 27, absolute value of x, radical 5x. Now, are these like radicals? They are like terms. They have the same exact variables and radical expressions. So we can just look at the coefficients. 77 of these minus 27 of these gives us 50 as absolute values of x, radical 5x is. This one was quite complicated. I'm pretty sure I threw that in there just so I could remind you of the absolute value of x thing. Questions on this one? Okay. Last thing then. Example 3. Hey, it's only been 17 minutes. Example 3, rationalize the denominator of the expression. Rationalize the denominator of the expression. So rationalizing is what we do to justify inappropriate action. Right? No, I'm just kidding. All right. So that, rationalizing is what I do at night when I'm like, I can have a second bowl of ice cream. Yes, of course I can. I worked so hard today. I deserve it. No. So in math, rationalizing is removing a radical, or not removing so much as making a radical resolve, making it clean itself up so it's no longer in its current location. Rationalizing is something we do in calculus all the time to help us do what we do in calculus, which is take derivatives and integrals. And you don't know what those are, but that's okay. So sometimes we rationalize denominators, which is what we're doing here, because you can see that in both of these denominators, we have radicals. What we want to do is take those radicals, get rid of them in the denominator. They're going to move up to the numerator, where they can be dealt with a little more easily. But in calculus, actually, sometimes we do that in reverse, and maybe we rationalize the numerator. We take a radical from the numerator, and we basically move it to the denominator using some algebra. Okay, I like to say resolve the radical. Make the radical clean itself up. Now, how do we do that? On this first one, we have 8 over the cubed root of 2. What I want to do is I'm going to multiply top and bottom by something so that this radical works itself out. It's a cube root of 2. How many 2's would I need so that it would clean itself up?
3.
I need 3 total, right? And so how many more do I need? 2 more. So I'm going to multiply by the cube root of 2 times 2. The cubed root of 2 times 2. Now, it has to be under a radical. What is the cube root of 4 over the cube root of 4? 1. So by multiplying top and bottom the same thing, I'm really just multiplying by 1, and that's not going to change the value of what I started with since it's really just a 1. And you'll notice here now what we get is a giant cubed root of 2 times 2 times 2 in the denominator. And in the numerator, we get 8 times the cubed root of 4. I'm just going to go ahead and multiply those 2's together. What happens in this denominator now? Yeah, you can simplify it. So we got a bunch of 2's there. So what gets to escape? Yeah, 2 comes out of the denominator. And I can't really do anything with that numerator, but you see how the radical changed location, right? Now we have a radical in the numerator, but we don't have anything in the denominator. This is a great answer, but what's wrong? It's not reduced. So here we have some regular old plain numbers. 8 and the 2 reduced to a 4. So 4 cubed roots of 4 is a fantastic answer. And again, this is something you can check on your calculator. So I'm just going to show this really fast. 8 over the cubed root of 2. 8 divided by the cube root of 2. The cube root is under the math button on a TI. Under the math button, number 4 is the cube root right there. And the cube root of 2, there it is. And you get 6.349, yada, yada, yada. I can type in 4 with, math. There's my cube root again right there at number 4, cube root of 4. So I'm going to take my original and my answer and compare them. And are they the same? Yeah, because they're supposed to be equal to one another. That's what that equal sign means. What you started with and what you end should be equal, okay? But they look totally different, right? Very different. It's a great way to check answers on your calculator, okay? What you start with should be the same as what you end with, and you'll know you did it right. Okay. Over here, there's one difference between these two problems. This denominator is what we call a monomial. Monomial. What is a monomial? One term. Very good. Think mano y mano. One-on-one. This is one term. Just the cube root of 2. What's this denominator? A binomial. Very good. Which would be 2 terms. 3 plus a radical 7. So this is a binomial. Now, when we're trying to rationalize a binomial, we have a slightly different way to do that. I am still going to multiply top and bottom. Does anyone know? Yeah, so it's 3 minus radical 7. This is called multiply by the conjugate. The conjugate, as in conjugating verbs. You change, the root stays the same, but you change a little ending, right, when you conjugate verbs. The only thing we change is one sign. One sign. Not all the signs, just one sign. You change one sign in the middle, and it'll work out perfectly. So we're going to multiply top and bottom by 3 minus radical 7. Now, when we multiply by 3 minus radical 7, how are we going to do that in the numerator? Distribute? Yes. Distribute is easy. So we're going to distribute the 2. What do you get when you distribute the 2? 6 minus 2 radical 7. Very good. Now, in the denominator, it's a little more complicated. What do we have to do in the denominator? Super distribute, or FOIL. You could say FOIL. Again, you've got to distribute. The 3 gets distributed, and then we got to distribute the radical 7. So watch what happens here. We're going to distribute the 3. 3 times 3 is 9. 3 times negative root 7? Negative 3 root 7. Very good. And we need to distribute the radical 7 to both terms over there. So we've got radical 7 times 3. Positive 3 radical 7. Very good. And then radical 7 times negative radical 7 is? Negative radical 49. Very good. 7 times 7 are both under the radical, and they just stay under the radical. But what is the square root of 49? Oh, nice how that works out. Okay. So we have in the numerator 6 minus 2 root 7 over what is the glorious thing that happens when we multiply by the conjugate? Yeah, these add out. These cancel out. Like terms, we've got a negative and a positive 3 radical 7. They add to be 0. And we know that this negative radical 49 is really... Oh, 7. Yeah, sorry, I was a step ahead of myself here. Radical 49 is 7. It's got a negative in front. So 9 minus 7 is 2. And this is a great answer, but it's not the correct answer that you would see in like one of my choices on the test. What's wrong? It needs to reduce. So this is a favorite wrong answer. What's wrong?
Oh, it's in the
2 divided by 2. Very good. This is the wrong thing right there. My favorite way to reduce these kinds of things is to ask you, what is this 2 dividing? Everything above it, okay? Each term above it. So I always encourage my students to write things out. Separate those two fractions. Divide each term by 2, and you will always reduce correctly. What is 6 divided by 2? 3. And then your 2 and 2 reduce to a 1, radical 7. And there is the final answer. My entire job is to catch mistakes like this. Be careful. My tests are hard. Do you have questions? Okay. You guys can start working on